Okay, we're now in section 04, which discusses counting techniques. An outcome is the result of a single trial of a process involving chance, called a probability experiment. The set of all possible outcomes of such an experiment is called a sample space. When you need to know the total number of outcomes, you can use the fundamental counting principle. So that's what we're after today. The fundamental counting principle says or states, suppose that two events occur in order. If the first can occur in m ways and the second in n ways after the first has occurred, then the two events can occur in m times n ways. In other words, you take the total number of possible outcomes for the first event and you multiply it by the number of ways the second event can occur, and that gives you your total possible outcomes. Examples that we're about to solve are things like this. How many ways can you choose a pair of socks and a pair of shoes if you have 5 pairs of shoes to choose from and 11 pairs of socks? If license plates have 3 letters and 3 numbers, how many license plates can you make? In how many different ways can a race with 6 runners be completed? Assume there is no tie. We will solve all 3 of these problems using this fundamental counting principle. Okay, how many ways can you choose a pair of socks and a pair of shoes if you have 5 pairs of shoes to choose from and 11 pairs of socks? We will use the fundamental counting principle to solve this problem. First thing we need to consider are how many ways can you choose a pair of socks? There are 11 pairs. Now this is what the fundamental counting principle says to do. It says take the number of outcomes for the first event and multiply it by the number of outcomes of the second event. So the second event is how many ways can you choose a pair of shoes? We have 11 times 5. There are 55 different ways to come up with different outcomes with 11 pairs of socks and 5 pairs of shoes. Okay, another type of problem we could use the fundamental counting principle to solve is a problem like this. If license plates have 3 letters and 3 numbers, how many license plates can you make? You need to consider if you are going to allow the letters and numbers to repeat or not. So that is kind of a big idea here. How many plates are possible if the letters cannot be repeated, but the numbers can? So the first thing you ask yourself, the first of the 6 items, how many letters are there in the alphabet? There are 26 letters in the alphabet. Now, if letters cannot be repeated, you will multiply it by the next number of 25. Why 25? Because after a letter is chosen in the first slot, the second slot only has now 25 options. We will continue this going down to 24. Moving on to the numbers, the digits. 0 through 9, there are 10 digits. Single digits, 0 through 9. If you were to count it out, 0, 1, 2, and 3, etc., you will have 10 digits. Now, it says that the numbers can repeat. So you would take 10 times 10 times 10, multiply it out, and you would have your answer. Okay, let's continue. How many plates are possible if letters can repeat? So now the letters can repeat, meaning if we have 26, we choose a letter, we can use that exact same letter again. And the numbers, we would assume from the previous example, they can also still be repeated. So with your calculators, you can take 26 to the third power, clean that up a little bit, 26 to the third power times 10 to the third power, and get a value for that. When numbers or items can be repeated, the number of outcomes will be drastically larger. And that should make sense because the less the smaller the numbers, the lower the product. The larger the numbers, the larger the product. In how many different ways can a race with 6 runners be completed? Assume there is no tie. So the fundamental counting principle can be applied here as well by answering the question of how many choices are there for first place. If you have 6 runners, there are 6 options or 6 different ways for these 6 runners to finish in first. And then we multiply it by the next outcome. Once a runner has passed the finish line and comes in first place, now there are only 5 runners left to come in second place. And so on. We continue this until we get down to the last runner. And we can multiply all of these together and find that there are 720 different ways for us to, for 6 runners to complete a race. So something that we need to talk about is called factorial notation, which is the product of the n natural numbers is denoted by n with an exclamation mark. You have an n with an exclamation mark, and it is called n factorial. The previous slide with the 6 runners, when you have something like that, when you start with a number and then you start multiplying by the number minus 1 all the way down to 1, that's called factorial notation, which we could have written like so. From the previous slide, 6 with an exclamation mark, we call that in math 6 factorial. So this would be 4 factorial. This would be 2 factorial, and so on. 6 factorial starts with the number 6, and we go down by 1 until we get to the number 1. 720. 4 factorial is 4 times 3 times 2 times 1, which is 24. You get the idea. 3 factorial, 3 times 2 times 1, which is equal to 6. Factorial notation is very important for what we are about to discuss. So now that we know what factorial notation is, we could use that idea to apply it to permutations and combinations. So let's talk about what a permutation is. A permutation of a set of distinct objects is an ordering of those objects. An ordering. Which means that the order matters in how you arrange something or how you choose something from a pool of n objects, which is the next sentence. The number of permutations of n objects taken r at a time can be written with this formula. This formula has n factorial on the top, and on the bottom it has n minus r factorial. It's easiest to just jump into an example problem. So here it is. To understand what a permutation is. If a company's board of directors has 9 members, how many ways can it choose a president and a vice president? Does the order matter in which a president and a vice president is chosen? If Mr. Tagani gets elected as president and Mr. Long is as vice president, are those distinguishable roles? Are they different from Mr. Long being president and Mr. Tagani being vice president? Absolutely. In situations like this, we will use permutations And the formula for that is here. Well, how do you know what n and r represent? Well, n is the bigger number. It's the pool of things or people or objects that you were choosing from. In this example, n is 9 because there are 9 members in this board of directors. And how many are we choosing? R represents the amount that you are choosing from the pool. From the pool of 9 members, we need a president and vice president. So our R will equal 2. So let's take n equals 9 and r equals 2 and plug it directly into our formula. The first one is n. The second number is r. N factorial goes on the top. And then the difference of the two, n minus r, 9 minus 2, is 7 factorial. And if we were to list out 9 factorial times 8 times 7 all the way to 1, this is what you would see. And then in the bottom, 7 factorial. 7 times 6 times 5 times 4. What you will find out is that the 7 factorial, the entire thing on the denominator, will cancel off. And you will be left with 9 times 8. There are 72 different ways to choose a president and a vice president from a board of directors of 9 members. Okay, combination versus a permutation is any subset of a larger set in which the elements of the subset can be in any order. In other words, the order does not matter with combinations. The order doesn't matter. And the only difference between the permutation formula and the combination formula is this r factorial in your denominator. So to recall here, the permutation formula has n factorial on the top, and then the difference between n and r factorial on the denominator. So the difference between the two, as I said, is this extra r factorial. The example problem that's shown says if a company's board of directors has 9 members, the same 9 members from the previous example, in how many ways can a committee of 3 people be chosen? In a committee, it does not matter who is chosen first, second, or third. There are no positions that are distinguishable from one another. So this is the big idea behind a combination. If a committee is chosen and there's nothing that says anything about a president, vice president, a chairman, things of that nature, we will jump right to the combination formula. So out of 9 members, in this example, n equals the 9, we are choosing 3 people. And so in our formula, n factorial is 9 factorial on the top. 9 minus 3 here is 6. This becomes 6 factorial. And then you have your 3 factorial here as well. So this represents my 3 factorial. This represents my 6 factorial, but it gets canceled off, reduced on the top, and all that's left is 9 times 8 times 7 divided by 3 times 2 times 1, which is 84. Okay, some guidelines here for solving counting problems on your homework this evening and on the test next week. The first thing is to consider the fundamental counting principle. When consecutive choices are being made, we will use the fundamental counting principle. One thing happens, and then another. The second thing that we always need to consider is Pretty much on every problem, you have to ask yourself, does the order matter? If it matters, we're going to use the permutation formula. If it doesn't matter, the order doesn't matter, we will use the combination formula. All right, let's jump into some example problems. Let's dig a little deeper here. Number 2, a group of 25 campers contains 15 women and 10 men. Part A asks, in how many ways can a scouting party of 3 women be chosen? The first thing we ask ourselves is, does the order matter in which these 3 women are chosen? No, it doesn't. A scouting party doesn't distinguish anything about roles, so therefore we will use the combination formula. How many women are there in this camping group? There are 15 women. That's our pool, 15 women to choose from. And we are choosing or picking 3 for this scouting party. Now, on to our formula for the combination. N factorial on the top, R factorial followed by the difference of 15 and 3 factorial. 15 subtract 3 is equal to 12 factorial. Okay, so we continue on. To simplify this, we will write it out. 15 times 14 times 13, and I want you to stop at 12 factorial right there. Because you have 12 factorial in your denominator, we will be able to reduce that with the 12 factorial on the top. The last thing we need is our 3 factorial, which is 3 times 2 times 1. So with the calculator, you can type it in 15 times 14 times 13, all of it divided by 3 times 2 times 1, which is 6. So 15 times 14 times 13 is 2,730 divided by 6. 455 different ways to choose 3 women for the scouting party of 3. Part B, in how many ways can a scouting party of 2 men be chosen? If we have 10 men to choose from, and we're picking 2 of them, let's jump right into our formula. 10 factorial on the top, 2 factorial in the front, and then now the difference of 10 and 2 factorial. We'll write it out. 10 times 9 times 8 factorial over 2 times 1 times 8 factorial, because they will reduce to 1, and we're left with 10 times 9 divided by 2. Well, what's half of 90? It's 45 different ways for a scouting party of 2 men to be chosen. Now in part C there, it asks, in how many ways can a scouting party of 3 women and 2 men be chosen? So what we need to do is take the answer from part A and multiply it by the answer we got in part B. Now why are we multiplying? Because that's what the fundamental counting principle tells us to do. One event occurring times another one occurring. And let's get our calculators back out. 455 times 45 is 20,475. And that is our answer for part C. Now, number 3 says, from 20 raffle tickets and a hat, 4 tickets are to be selected in order. The holder of the first raffle ticket wins a car, the second a motorcycle, the third a bicycle, and the fourth a skateboard. In how many different ways can these prizes be awarded? Does the order matter in which the winners are selected? Absolutely, yes it does. Winning a car is very different than winning a skateboard. So let's go through this. Of 20 raffle tickets, permutation of the 20, we are choosing 4 winners. My permutation formula says to take n factorial, put it on the top, and divide it by the difference of n and r factorial. 20 minus 4 is 16 factorial. So here we are. We're going to list it out. 20 times 19, 18, 17, and we will stop at 16. Why 16? Because that's what's in my denominator. And they will cross each other off. So with your calculators, what we need to accomplish is 20 times 19 times 18 times 17, which is 116,280 different ways for winners to be chosen. The fourth and final example problem for this set of notes is a committee of 7 people consisting of a chairman, a vice chairman, a secretary, and 4 other members is to be chosen from a class of 20 students. In how many ways can this committee be chosen? What we need to first consider is, does the order matter? Well, we have a couple things taking place here. A committee of 7 people needs to be chosen. So we need 7 total people to be chosen out of how many? 20. But let's dig a little deeper. This committee needs to consist of a chairman, a vice chairman, and a secretary. Those are distinguishable roles. Permutations come to mind. And 4 other members. No distinguishable roles, combinations come to mind. This and tells me to use the fundamental counting principle. So we will have a permutation multiplied by a combination. Should add up to 7 total people. So let's do that. The first committee, or excuse me, the first grouping here is the permutation. We have 20 people to choose from to find ourselves a chairman, a vice chairman, and a secretary. 3 distinguishable roles times the combination. After these 3 people get chosen, the total number of people go from 20 down to 17, and we're trying to find 4 other members for this to happen. So let's jump into our equations. For permutations, we take n factorial on the top, and then the difference between the two, factorial, n and r, on the bottom, times 17 factorial on the top, 4 factorial on the bottom, times the difference of n and r. The difference of 17 and 4 is 13 factorial. So here we go. We can go ahead, you can cross-reduce if you like, leaving us with 20 factorial on the top and 13 factorial along with 4 factorial on the bottom. So what I'm going to do is take 20 times 19 all the way down until I get to 13. Once I get to 13, I can stop. Okay, 13 factorial. I could stop there because it will cancel off and reduce with the other 13 factorial on the bottom. Now, I also have 4 factorial. Can't forget about that. So I write it out. And now we get our calculators out. So 20 times 19 times 18 17, 16, 15, and now 14. All of that will be divided by 4 times 3, which is 12, times 2, which is 24. We will divide 390,700,800 divided by 24, and our answer is 16,279,200. That's my answer for question number 4.